Good afternoon, Mindsetters, and welcome to it. It's another beautiful session of Mindset Learn Extra on a Tuesday afternoon. I am Katlego, and of course, we're going to be together till the hour. And of course, we're going to be making sure that we thrash all of those questions that you bring forward to us. Anything but physical science. I'm not alone in the studio as usual. I'm with my awesome teacher. Say, how are you doing?
I'm really well, Katlego. It's John here, and I'm really pleased that you're with us this afternoon, Katlego. I really hope you enjoy it as well.
Awesome. And you know, get in touch with us on Facebook. We are facebook.com/Learn Extra. On Twitter, we are at Learn Extra. And our website is up and running. It's www.learn.mindset.co.za. You can go there to access all of your previous notes. And just one thing important, today's notes are going to be posted on our Facebook page. It's facebook.com/Learn Extra with an X. As usual, I come bearing gifts. It's a beautiful competition that we are advertising on the show today. And you stand a chance to win a beautiful Casio calculator, you know. And for you to get yourself this beautiful Casio calculator, you just have to go to our Facebook page. The link is there. Just click on it and answer as many questions as you can. And that question, you stand a chance, of course, to win this beautiful Casio calculator. And John, over to you.
Thank you so much, Katlego. Great, guys. I hope you're ready for this. Now, remember last week we started off talking about aqueous solutions and how things dissolve in this magical stuff which we call water. Of course, we can't do without it. And so I want to remind you about the importance of water. Water, really important, Katlego.
Water is very important. You know what they say? Water is life. So
absolutely. So, guys, we want to bring your awareness to the issues around water. And so in our curriculum, we're dealing with the many different types of chemical reactions that take place in solutions. Now, did you know that we wouldn't even be able to talk to you here if it wasn't for some of those reactions that are taking place in your body? Now, blood, the nerves, all of them depend, even your brain, depends on chemical reactions taking place, and they're all taking place in aqueous solution. Aqueous, remember, is when things are dissolved in water. So what we're going to do this afternoon in this lesson is we're going to identify different types of reactions that take place in aqueous solution, and then we're going to do something really cool. We're going to use our knowledge and apply our knowledge of solubility, the ability of things to dissolve, to identify unknown ions present in an aqueous solution. So guys, we recognize sometimes we've got some water in a glass. Well, what else is in there? We can't see it. Yeah, maybe we can taste it. But is there another way of finding out what's inside, particularly if something isn't very good for us? We don't want to go around tasting stuff just to find out. There's not a very good chemical test. So we want to set up some chemical tests that you can do and that you can start to identify what's happening inside water. And this is really important for the environment as well. So let's go to the challenge question now, and I want to remind you about the challenge question, which is the same as the challenge question that we had on the board last week. We're just going to go over it because I think it's really important for us to stress this. It's told that a sample of water is taken from a stream in the Middle Olifants catchment area. Now, the sample is found to have high levels of compounds found in fertilizers, high levels of bacteria, and undissolved organic products. What actions would you take, would you recommend to water management in this catchment area? Now, guys, the reason we put that question there, the reason we want to just go over it again is to remind you that there is a national water game challenge. And it's the first time that we're running it in the country. It's been run in other parts of the world, but in 2014, it's the very first time that we're running a water game challenge. And it's a serious game because it deals with the serious issue of how we're dealing with water. Yeah, this challenge question is important, but the more important thing is that we can start to talk the conversation about water and what's the role of water and what's our attitude to water. So get on the game. How do you do that? You go to watergame.co.za, register, and you'll be amazed to see how many prizes there are. There's some great prizes, Katlego.
Indeed.
And anyone can enter. Doesn't just have to be a grade 10 learner. It could be a grade 11. Get your granny, your auntie, anybody can enter and anybody can play. Now, it doesn't take a long time either. So if you go, it's a turn-based game. What that means is you've got 12 turns to get the highest score. You make strategic decisions, like what we've said here. You improve the environment. You make sure there's enough food and water for the people and that they've got enough jobs. So it's a multidisciplinary approach to dealing with the simulation. So I hope you get on and play it. And maybe you're on it. Okay.
On it.
I can see that Katlego wants to get some money out of this. Remember, it's only until the 18th of August.
Yep.
So you've got to make sure that person that's on the leaderboard on the 18th of August, they're going to get the big check. But guys, you don't have to wait for the 18th of August to be a winner. As you're playing, there are spot prizes. There's airtime. There are tablets. There are other things that are being given away. And they're going to be adding to that. So guys, look out on the page. Get going. Get playing. Unfortunately, this game has to be played on a PC. Has to be played on a computer. And you have to be connected to the internet. It's an online game. So hope you get into it, and I hope you enjoy it. Right, that's enough of the water game. Let's get into our summary for today. Now, guys, the link to the notes, not the notes that you see on the board, but the notes that you can print and you can revise and use them with all the questions. They're on they're on Facebook. So get that link. It will take you to a page. You can either download them or view them. It's on a mobile-friendly site for downloading. You need a PDF viewer, but you can view them on a feature phone. So there's the link there. So let's go through the major types of reactions you're going to need to know. So you should be able to identify the following types. Ion exchange. So when we talk about ion exchange, guys, this is not difficult. We recognize in water, we've got ions. You've got cations, which are positively charged, and anions, which are negatively charged. And they're all swimming around together in the solution. Now, what sometimes happens is they have preferred partners. I'm sure this might have happened to somebody like Katlego. Katlego, you've been on a couple of dates before, haven't you? I'm sure. You've lined them up and you've taken a partner to a date, and maybe one of your friends has come along and he's got a partner that's he's interested, but actually you prefer his partner and he prefers your partner. It's happened.
It has happened.
It's happened. And so what happens? What do? You swap dates halfway through the evening, and you have a really nice time. So that's ion exchange for you. It's the dating game of chemistry. So what we start off with is two solutions, and we mix them together. And what often happens when we get ion exchange is we get a precipitation. So an ion exchange and precipitation reaction are quite similar. What's interesting is that ion exchange is used for purifying water. It's used in extracting things like gold in the gold process. They use ion exchange in a number of different industrial ways. So it's swapping ions. So you might start off with AB together, and they get mixed together with CD. And if this is an aqueous solution, and we take that in aqueous solution, and at the end of the process, what we would have is A links up with D, and C, the cation C, links up with B. So they've just simply swapped. Now, one of these could remain as aqueous. It's not normal that would remain as aqueous. One of them would probably be a solid, but they kind of tend together like that. When we get a precipitation means something falls. So when we're talking geography about precipitation, we say, what type of precipitation are we expecting today? Is it rain, or is it snow, or is it hail? All of those are precipitations, things that fall from the sky. But precipitation in chemistry is things that fall in the solution and they go to the bottom. So they form a layer at the bottom of the test tube that is a solid. And it's very similar to the ion exchange, and I'm just going to change the one thing that will happen is that when we've got a precipitation reaction, we will have a solid in it. And those solids can have different colors. Just a layer at the bottom could be white, it could be orange, it could be yellow, and they're very good indicators to us of what might have been present. We can use those. Now, the other type that you need to know is something called a gas-forming reaction. Now, the most common gases that are given off in aqueous solution, list a couple for you. There's carbon dioxide, CO2, there's hydrogen, there is oxygen, there is sulfur dioxide, and the list goes on. In this case, what we've got, two solutions added together, you shake them together, and whoosh, you get some gas coming off. A really nice one that you can even do at home is if you take, and I know that people have done this, so it's not a surprise, but if you take some bicarbonate of soda and you make a solution with it, and you take some vinegar and you make just straight white vinegar, put that into another cup, take the 2 cups together, and you mix them together, guess what happens? It froths up and it bubbles up and it makes a really great mess. It makes an even uglier mess if you put some food coloring in it. Please don't use your mom's best china to do this, but it is a lot of fun. There are things on YouTube with things like Mentos and Coke that are gas evolving reactions, all happening in solution. Now, acid and base. Now, guys, this one is a serious one. The acid and base reaction, you're going to need to work with these from grade 10 all the way through to grade 12, and it's become a really important part of the grade 12 exam syllabus. So make sure that you understand what an acid is, what a base is, and what the difference between those. Now, common acids that we know about are things like hydrochloric acid, HCl, nitric acid, HNO3, and sulfuric acid, H2SO4. Those are the 3 strong acids that we deal with at school level, and they're really common. Now, if we have one of those reacting with a base, something like, let's change the color, something like sodium hydroxide, something like potassium hydroxide, or even an oxide like calcium oxide, that would be an acid-base reaction. So when things that have a low pH, measure of acidity, react with things that have a high pH, you join those 2 together, you get neutralization. It's an acid-base reaction. Okay, water is the critical thing here. Water keeps a balance, and water is the middleman. It's neutral, has a pH of 7. We talk about pH, and in grade 12 we'll define and work out pHs, but we're not going to do that just yet. So acid-base reactions, I think I've said enough. You'll learn more about it in grade 11 as well. Now, electron transfer reactions. Now, I'm not going to go into too much detail because you'll do a whole section on this later in the year. But simply to say is if we take something like zinc and we put it into copper sulfate, what ends up happening is that because zinc is the more reactive metal, what happens is that zinc wants to lose its electrons. So it swaps places with copper. And the end result is that we get some copper plus zinc sulfate. Now look what's happened. Is this was neutral to start with. The zinc was neutral to start with. And what's happened is that the zinc has donated its electrons. It's lost them. And it's forced copper to gain them. Copper wasn't just sitting without electrons. It was sitting as a 2+ ion over there in the solution. And it's been made to accept them. And now we've got zinc 2+ plus the sulfate, which was 2-. Nothing has happened to the sulfate. It's just bonded nicely, attracted with the positive cation, and the sulfate is the negative anion, and they pull together. These are in aqueous solution. They're swimming around in the water, and we could even say that the zinc is now an aqueous solution, the copper is an aqueous solution, but this, the metal copper, is a solid. The zinc over here was a solid to start with, and there's been a transfer of electrons. Call that a redox reaction. Now guys, we've almost out of time, but there's one last thing that I just want to deal with, and this is very important. So we're going to run through this very quickly. And it's what we started last week, to discuss solubility. And I'll explain to you why now, because we've got these tests on solubility that are used to identify unknown things. So you need to learn them. There is a whole table of them with more examples in the notes, but I just want to run through these ones. So if we have a nitrate, solution of nitrate, they're all soluble. Doesn't matter what it is, they're all soluble. So all nitrates are soluble. All carbonates, these are insoluble, but there are some exceptions, and we're going to say except, and I'm going to leave it there for the moment because we'll come to them. Sulfates, they're all soluble. The sulfates, these are the ones that you've got to be a little bit more careful with because there are some exceptions. So these are all soluble. That means they all dissolve, but there are some exceptions. The ones that don't dissolve. And here we're going to talk about calcium, we're going to talk about barium, and we're going to talk about lead as well. Lead's not very soluble in most things. Chlorides, all are soluble. All soluble. But the one that we're really interested in is the exception. And the exception here is silver and to a certain extent mercury. But we don't really worry about mercury. The silver is the important one. And then the last thing, which we'll come back to this, these are all soluble. Doesn't matter. Now notice group 1 ions, these are metals, so they will be cations. And ammonia is NH4+, so they have a plus charge. So they're all soluble. There's no exception to that. But because those are all soluble, we can say the exception is here, even the carbonates, except group 1 and ammonium. Okay, so guys, I hope you've got those solubility rules. Make sure you get a hold of them. We'll be referring to them when we come to the questions. Katlego, I know I've gone over time, but I just got carried away.
It's okay, man, as long as that information just stick in there, and we forgive you.
Okay, thanks.
Remember to go to our Facebook page. It's facebook.com Learn Extra with an X to access all the notes that you might need. There are links there that will direct you, of course, to our website. And that's where, of course, you can also get a link to win this beautiful Casio calculator, proudly sponsored by Casio. We'll be back from ad break after this. Welcome back, Mindsetters. I'm still Katlego, and of course, I'm with John, my teacher, where we just, more or less making sure that we feed you with all of the information that you need to help you prep and study for those exams. It's physical science time. And as usual, as you heard him before, we have a beautiful, beautiful competition that we're running. It's a water game competition where you stand to win, or you stand a chance to win various prizes ranging from 5,000 to a trip to a game reserve of your choice. And of course, you can also win a bursary to go study at the University of KZN. Just go there to the water website, www.water competition website.
It's Water Game.
Water Game.
Watergame.co.za.
Watergame.co.za. Thank you, John, there. And you can just play along, invite all of your families and friends, and you'll stand a chance to be the Mindset winner. Over to you, John.
Thanks so much, Katlego. Great, guys. Now, we're going to have some water games this afternoon right here in studio because we're going to be doing some tests of some samples of water. And we haven't really got time to do this practically, but I want to talk to you about how you could get asked this in an exam. So we're going to simulate it as well and go through it. So what we're starting with is the idea of having some silver nitrate. Now, silver nitrate reacts with a sample of potassium chloride, which is called sample A. sodium iodide, which is sample B, and lithium bromide, which is sample C. So guys, here we've got it. We've got 3 test tubes. If I had to draw them, just let's make some space here and let's get some pictures going. So here we've got sample A, sample B, sample C. Now remember what they told us was that the first one, sample A, was potassium chloride. So I'm going to put down KCl. And then this next one was a B, sodium iodide, and the last one was lithium bromide. So sodium iodide and lithium bromide. Okay, and we've got these in a little test tube like that, and now we add a few drops, just a few drops of something called silver nitrate. So there we go. So we're putting some silver nitrate into that, we're putting some silver nitrate into that, and we're putting some silver nitrate into that. And what I want you to understand is that we've got to apply our solubility rules here. Remember, we said that all nitrates are soluble. So we know that these drops of nitrate, of silver nitrate, they're soluble, they dissolve. And we know these are group 1 metal cations, so they're soluble. So there's going to be no bits and pieces. But look at something interesting. If I add silver to sodium chloride, silver nitrate, I'm going to add silver ions, Ag plus, and I'm going to have floating around in the solution some Cl minus. Now guys, what you need to understand is what we said about the chlorides. All chlorides are soluble except for the silver chloride. They don't like to dissolve. They're not very soluble at all. And in fact, what happens when these two get close to each other, they kind of stick together. Okay? And I've stuck them on top of each other. It's not really right to stick them on top of each other, but let's hope that we can just stick them next to each other like that. We're going to make some silver chloride. And silver chloride is a white precipitate. So at the bottom of the beaker over here, we're going to make a whole lot of milky stuff, and the solution is going to go white. Okay, that's what we're going to see if we add silver nitrate to potassium chloride. We were asked to predict what else would happen. Predict what you observe for each of the other samples. Now, if you have your notes in front of you, then we'd be able to say, well, what will happen if we have silver nitrate and sodium iodide? Now, all the halogens are, all the halide salts of silver are not very soluble. And they're different colors. The silver chloride is white in color, the bromide is a creamy color, and the iodide is a yellow. It's almost like a canary yellow. It's very nice to see. And so we're going to shade that in and say, you would notice at the bottom of this test tube is a yellow precipitate. And in the last one, we're going to take the silver nitrate and we're going to add it to the bromide. Now I can't get the color right, and I haven't got the option to have more colors. Maybe I do. Let me see if I can get some custom colors. I want a creamy one. I want one that's a little bit over there, maybe a little bit less yellow. Maybe that's it. Add to custom. Let's see. Yeah, we're going to do that one. We'll say that's okay, and let's hope that we've got it. You know what? It's not working. I want that one. There we go. I've got it. And we've got a kind of not yellow and not white. And that's your bromide. Okay? But some people find it difficult to tell the difference between this one, and this one. And so chemists have done some experiments. And they've found some other tests that we can do to distinguish those. I've written about those in the notes. And let's see if we've got some chance to deal with that. So we've done our predictions. What would you observe? We'd observe precipitates forming. Look at what the next question says. Now, even if you didn't know those precipitates, I hope you can now deal with the balanced equation for the reactions that take place for each sample. So let's do this. Sample A, we know that we've got potassium chloride. We know that we've started with silver nitrate. What are we going to be producing? We know that these were in aqueous solution. That was aqueous. What are we going to produce? We're going to produce silver chloride. Valencies are the same. Silver is +1, chloride is -1, but they form a solid. And what's the other stuff that's still left in aqueous solution? Potassium nitrate. Is that soluble? Yes, it's very soluble. Remember what we said. All nitrates are soluble, and all salts of group 1. And potassium's particularly soluble. So potassium nitrate is very soluble. It's one of the most soluble things. If you compare other things, they might be soluble, but if you've got a group 1 and a nitrate, they're the most soluble. So look out for that. Okay, next we go to, that was in sample A. What about the equation for B? Well, in B, we had silver iodide plus sodium nitrate. Notice the balancing isn't a problem because they're all +1. And we just must put in aqueous. We must put in aqueous. And what we're going to say, we produce silver iodide, which is our yellow precipitate. That's the solid, plus sodium, not potassium. Let's read the question. Plus sodium nitrate. And that's aqueous. It dissolves. It's very soluble, and so we don't have a problem with it. Well, what about the next one? We made lithium bromide. We started with lithium bromide at least, and we're going to make some silver bromide. So we started with lithium bromide, and we added some silver nitrate, just a few drops, and that was in aqueous, AQ, standing for the fact that it's dissolved in water, and we made silver bromide plus some lithium nitrate, and that was still dissolved, aqueous, whereas the silver bromide was solid. Check everything is balanced, and yes, it is. So we've done the hard work. We've identified and we've written the balanced equation. Next question. Let's go. What type of reaction occurs in each? Well, this isn't that difficult, guys. Think about it for a minute. What have we done? We've taken 2 aqueous solutions, added together, and we've got something falling to the bottom. We call that a precipitation reaction. If you had said ion exchange, you would also not be wrong. So precipitation, ion exchange, precipitation is the more obvious one. Now, last one, identify the insoluble salts that form. Well, we've done that. We did it right at the beginning. We said that one in A was silver chloride. There we've got it. And in B, it's silver iodide. And in D, it's silver bromide. Easy stuff, but so useful. We could go to that stream in the middle of Olifant's catchment area, and we could take along some silver nitrate and start to test, are there excess chlorides, bromides, or iodides in the water, just by adding a few drops. Now, it's important to note that when you do this test, you also must add acid, because there is something else that is insoluble. Silver carbonate. We didn't have time to discuss this in our summary, but silver carbonate is very insoluble. It is insoluble. So what we need to do, it also messes up our results. It makes a white precipitate, and it interferes with our results. So what we've got to do is we've got to add acid. And if we add an acid, it will dissolve the carbonate and produce carbon dioxide. It will have a gas evolving equation. It'll produce carbon dioxide and the precipitate disappears. But if we add acid to any of these these precipitates, any of these, they're going to laugh at the acid. They're not going to disappear. They're going to stay there. But there's something I want you to think about. You need to make sure that you add the correct acid. Think about it. We added, to make it a fair test, we added silver nitrate. We know that silver chloride produces a white precipitate. So we must be very careful not to add any more chloride ions. We could use any acid, but probably the best one to use in this scenario would be one that doesn't have extra ions. So nitric acid would probably be my favorite. The one that you want to avoid, you would never use hydrochloric acid. Because if you used hydrochloric acid, and you added HCl here, you know what would happen? You would just get more white stuff forming. And then you'd be really confused, because not all of the silver ions would necessarily have precipitated. Now, I've been talking too much. Let's move on, because we've got another part to this question. So Paula, who was the person doing this experiment, can't decide if one of the precipitates is cream or yellow. Now, this is obvious. This is a common problem. We sometimes find that the precipitates aren't very distinct. If we've got a high concentration of the iodide ion, then it will be very clear. It will be canary yellow, and it stands out very nicely. But if there's not so much, and we could get confused. So what do we do? So she adds a few drops of carbon tetrachloride. Now, carbon tetrachloride is very poisonous, it's dangerous, and it's carcinogenic. Carcinogenic means that it can form cancer. There's been research to show that it's not a very good thing to use. So it's better that we do it just as a test on the board here. We can use alternatives like trichloromethane instead of the tetrachloro, but the trichloromethane is an alternative. The colors are slightly different with trichloromethane though. So this organic liquid forms a separate layer with the water. She then adds chlorine water and shakes the mixture. So the carbon tetrachloride turns pink. Now, I want to show you what's going to happen in this scenario. And it's really interesting, and it's a really nice thing to see if we can get this done. So here is our solution. And she couldn't make up her mind whether the original thing was cream or yellow. So she takes some of the original unknown. Notice that there's no precipitate here. So she's just taken from the original solution. And one beaker. And then she adds carbon tetrachloride. Now the carbon tetrachloride is more dense than water, and it forms a layer that's separate at the bottom. So there's my carbon tetrachloride, CCl4. In here is my unknown. I don't know what it is. I suspect it could be a bromide or an iodide, and I'm not sure. This is my unknown. And the next thing that she does, she then adds chlorine. Chlorine water. Chlorine dissolved in water. Now, chlorine is a very strong oxidizing agent. It's one of the more reactive halogens. And in fact, if we look at group 7 on the periodic table, you'll see it's fluorine, chlorine, bromine, and iodine. And that's on group 17 or group 7. We call it 17 at the moment. These are halogens. And what we recognize is that they are all wanting to gain an electron. So if we put them in, they're going to take electrons away from something else. So chlorine is more reactive. So if there is bromine in it, or if there is iodine in it, then chlorine comes along, and look what it will do. If there was a bromide ion, which is sitting happy and comfortable because it's gained its electron. It's in a neutral state, just like the noble gases. It's got to be like the noble gas at number 18, filled outer level. Chlorine comes along and says, it's not fair. You've got the extra electron. I'm going to take it from you. And so chlorine takes the electron away from the bromine, and we're going to need 2 of those. And chlorine then becomes chloride, and there are 2 of chlorides, and bromine has got no alternative but to turn back to Br2. Okay, so that's the process. This is what sort of reaction? Transfer of electrons. It's a redox reaction. Now the interesting thing is that the bromine, if it's non-polar, and we spoke about polar and non-polar last week, and what we know is carbon tetrachloride is non-polar. So bromine dissolves very easily in the organic layer, and it turns a nice color. The difference between these two, the reaction, if it was bromine, would do that, will produce bromine. If it was iodine, would be exactly the same chemical process. Chlorine and iodine, sorry, let's just correct that. We'd have iodide ions present. Iodide, 2 of them. Chloride, the chlorine would become chloride, and the iodine would become the iodide would become iodine, and this dissolves in carbon tetrachloride and gives us a pink solution. So in the question, what we were asked is what substance caused the organic layer to turn pink? It was iodine. Iodine. Where did the iodine come from? It came from this redox reaction. I want to finish the question. Redox is the answer. Write a balanced chemical equation for the reaction, and I've done it already. There it is. Hope you can see it. There it is, and we're done. Well, sorry, we've got over time a little bit again, but I'm sure that that's been interesting. Katlego, over to you.
It is so, so fascinating, John. So that's why I just kept on, looking at you and going, okay, dude, go on and on and on. It's okay. But then, of course, mindset is remember that the Water Game Challenge is on, where you stand a chance to win great, great prizes, ranging from the grand prize of 5,000 Rand for a winner and a trip to any national or reserve a destination of your choice with your family. So just make sure that you go there and then you enter the competition. On Twitter, of course, it's hashtag #SAWaterGame. And you can get the link to that or the hashtag handle there on our Twitter pages at Learn Extra. We'll be back with more and more of physical science after this. Welcome back, Mindsetters. You're still tuned in to Mindset Learn Extra. I am Katlego, and I'm not alone. I'm with John. And, it's a beautiful, beautiful day where we're just running competitions left, right, and center. I must remind you that before we wrap up the show, I'm going to be giving you the winner of the Casio calculator from last week. But then if you want to be like him or her, just make sure that you go to our Facebook page. There's a link there. And then you more or less have to make sure that you test yourself as much as you can, and the one who answers the most questions correctly, thank you very much there, John, stand a chance to win the Casio calculator, proudly sponsored by Casio. John, let's wrap this up.
Katlego, thank you. Guys, test yourself is really important. There are only 5 questions, but take your time. But don't take too long. Competition closes next week on Tuesday, 8 o'clock in the morning, and if you do the test yourself, you will get your score and you will get your results as well. You'll be given the right answers. So it's not just about entering to win the calculator, it's entering to make sure you are learning. And these questions, some of them are a bit tough. So if you get something wrong, drop us a line. From last week, if you didn't get something right, you're still not sure, put it on the help desk. Say to us, I don't understand why this is the wrong answer. So make sure you play a proactive role in your process of learning. Okay, now we want to just take a look at the challenge question. And we've been talking about this water game. Guys, there's lots to talk about as far as the water game. So what would we be doing? What recommendations would we make? Well, I want to take a different stance this afternoon from the one I took last week, just to show you that there are other things we could do. What we could do is we could recommend to the water management people, recommend regular testing. Regular water testing. Because, you know what, maybe the tests weren't that accurate. Now, we've shown you just the silver nitrate test for testing for the halogens. But there are a whole lot of other tests, and in chemical industry, they actually use machines as well. They do all sorts of tests. But we need to understand regular water testing is important, because maybe it was just a bad day. Maybe the water situation isn't so bad. We need to monitor our water regularly. We need to make sure that we are purifying our water, that we're boiling the water if it does come from a stream, that we are treating it with water purification tablets to make sure that we get rid of the bacteria. The boiling will get rid of the bacteria. The filtering will get rid of the solids and other stuff. And if you had an ion exchange column, then you could pour the stuff through a column like charcoal column. It would absorb some of the stuff and it would give you purer water at the end. So we need to educate people about making sure that they don't drink dirty water. Water is very, very important. We've had some incidences earlier in this year where people and children particularly have got very sick, and some of them have even died because they drank dirty water. Please tell your friends not to drink dirty water. They need to make sure that water is purified. So a big education campaign, more testing, more research, more education, letting people know what they need to do to make sure that their water doesn't get polluted. Okay, so give us some ideas. I don't know if there are any comments on Facebook regarding the challenge question. Anybody's come up with some ideas. If you haven't had a chance to put your idea down, then put it down now, and we'll try and pick it up. Are there any?
John. We have one from Precious Mripsu Simelani. I'm sorry if I misspelled your name there. She's saying that I can recommend that they must keep the area around the catchment clean, store the water in a tank and clean it with chemicals, and you must make sure that you tell people not to throw all cans and plastic into the rivers.
Absolutely wonderful, Precious. That's a great answer. It goes quite a way to making sure that we're keeping our water resources ready for the next generation. Guys, we can't just be thinking about ourselves. Water is going to become more and more scarce. And for industry that uses these type of reactions that we're talking about today to make all sorts of products for us, they're going to need water as well. And if we don't have a steady supply of water that is usable, we're going to miss out. And our children are going to miss out, our grandchildren are going to miss out. We want to leave a legacy of a better earth than the one that the previous generation left with us. So guys, let's get together, let's make a difference, let's clean up the environment, and let's do something positive for the future. Okay, I want to just go back to the previous question because we finished question 1, but let's see if we can get on to question number 2. And look what it says. Also dealing with a chemical test. This time we haven't got Paula, but we've got Pretty. And Pretty adds a few drops of barium chloride to sample X and sample Y. One of these unknown solutions contains sulfate ions. She then adds hydrochloric acid to the mixture. Now notice something here. I told you don't use hydrochloric acid in the previous one, but we were adding barium chloride, and now we're adding hydrochloric acid. So we kept the unknown or the known ions the same. We're doing a fair test here, guys. We don't want to add things that are going to make an impact. So we added hydrochloric acid because we'd added barium chloride. If I'd added barium nitrate, I would add nitric acid. So be aware of that, just as a careful, something to be careful about. So here are the table, the table of observation. And what we notice in sample X, we got a white precipitate. In sample Y, we got a white precipitate. Quite interesting, eh? Both of them produced a white precipitate. She's then added hydrochloric acid. Notice chloride, hydrochloric acid. We're told that the white precipitate dissolves and bubbles of gas are released, where this one, in Y, the white precipitate remains. So, what do you think has happened? Let's think about it for a minute. We added barium, and we know that one of them is a sulfate. Tells us one of them is a sulfate. And we know that from our table of solubility, barium sulfate is insoluble. So barium sulfate doesn't dissolve. It forms a white precipitate. So this white precipitate that remains must have been barium sulfate. Well, then what was this white precipitate? Well, we know that it didn't remain dissolved, or didn't remain solid. It dissolved when we added an acid. So this one must have been barium carbonate. So we recognize it's released bubbles, and so I think we've more or less answered the questions. But that's just my thinking. Let's see what happens. What conclusions can she make about the anions present in sample X and in sample Y? So remember, an anion is a negative ion. Negative ion. Cation, positive ion. We're not asked about the positive ions. They don't have any role here in terms of the solubility of these substances. So what we are asked to do is to say, what can we say about sample X and Y? It just looks like we've got a little bit of a jump on the board, but let's see if we can get it. So sample X, we're going to say it had carbonate ions. Those carbonate, either like that, AQ, or we can write it out in words and say carbonate ions were present. In sample Y, what do we know? Well, I reckon that those were sulfate ions, SO42-, and they were aqueous. Remember, in the original solution they were aqueous, and these are sulfate ions. Before we added anything. Now, next, identify the white precipitate. And we've done that, are formed. We've done that already. When barium chloride was added, we've identified them. The white precipitates, remember, barium chloride, barium carbonate in X, and barium sulfate in Y. And I'm wrapping up when I say the next part of the question is, what alternatives could have been used if there was no hydrochloric acid? We could have used nitric acid. And guys, that's the end of my set of questions. I'm going to hand over to Katlego. Great being with you today.
It's been an awesome pleasure, man. Thank you very much. And I must say yay to our Casio calculator, grade 10 winner. Her name is Snentlantla Dlamini. Snentlantla Dlamini, congratulations. If you want to be like Snentlantla, keep, answering those questions keep answering those questions on our posted link, and we'll make sure that next week you walk away with a Casio calculator. It has been an awesome pleasure being with you, Mindsetters. Just make sure that you keep well, keep safe, drink water, and I must just, before wrapping it up, remind you of our beautiful, beautiful competition, water game competition. As I make sure that you more or less get to benefit while you keep healthy drinking those water. It's hashtag SA Water Games. Just go there, post on that, or click onto that hashtag. And on Facebook, of course, we are at facebook.com/LearnExtra with an X. And of course, on Twitter, we are at LearnExtra. Make sure that you interact with us. We are also active on our website. It's www.learn.extra.co.za. It's been an awesome pleasure, guys. Take care. Bon voyage. We love you.